Hello, everyone. I'm Donggeun, and I'm a math PhD student at the University of Rochester. It's my pleasure to give a talk at Harmonic Analysis People's presentation on YouTube, and I'd also like to thank to the organizers. So today I'm going to give a talk about Fourier restriction and well-approximable numbers. This is a joint work with Robert Fraser and Kyle Pembroke. So let's get started. So let mu be a positive Borel measure supported on a complex set in Rd. We consider the estimate LP norm of f d mu hat is smaller than L2 norm of f respect to the measure mu, where f d mu hat is defined as follows. If mu is a surface measure on a smooth manifold, for example, the paraboloid, cone, or the moment curve, the estimate is related to dispersive PD is. In this talk, we're more interested in when measure mu is supported on a fractal set, for example, Cantor set. So why is it interesting? This is a natural generalization because Hausdorff dimension of a smooth manifold is an integer, but we want to make it non-integer as well. So on a fractal set, Hausdorff dimension could be a non-integer. Also, if we find something interesting about measure mu on a fractal set, then since we are thinking of this on a broader perspective, this thing could be also applied to measure mu supported on a smooth manifold so that we can have a better understanding on those measures. And furthermore, it could give us a better understanding on related dispersive PDEs as well. In this sense, we are interested in measure mu supported on a fractal set. So let's look at Stein-Thomas theorem first. Let mu be a surface measure on the d-1 dimensional paraboloid for p greater than or equal to 2 d+1 over d-1. We have the following L2 LP estimate, and the range of p is optimal. The fact that the paraboloid has positive Gaussian curvature played a key role in the proof. But we can think of other measures. If mu is a surface measure on a smooth manifold, for example, the paraboloid, the cone, or the moment curve, we can use its geometric properties like dimension, smoothness, and curvature. If mu is supported on a fractal set, for example, Cantor set, then we cannot use such geometric properties. However, there's still a theorem that we can use. So it was proved by Mockenhaupt and Mitsis independently, and the endpoint result was proved by Bak and Seeger. Let mu be a positive Borel measure on Rd. Assume there exists A and B such that measure of a ball of radius r is smaller than r to the power of a, and mu hat is smaller than c to the power of negative b over 2. For p greater than 4d minus 4a plus 2b over b, we have the following L2 LP estimate. If p is a surface measure on the paraboloid, then a and b are both d-1. Thus, it recovers the range on Stein-Thomas theorem. So we can ask the same question in Stein-Thomas theorem. Is the range of p optimal? So in Stein-Thomas theorem, they considered a very specific measure on the paraboloid, but in the previous restriction theorem, for fixed a and b, there could exist many measures which satisfy the regularity condition and the Fourier decay condition. So we want to do the following. For each p smaller than 4d minus 4a plus 2b over b, we want to construct a measure mu such that mu satisfies given regularity and Fourier decay conditions, but L2 LP estimate fails. Also, from now on, we'll say A and B are exponents of the Fourier regularity condition and the Fourier decay condition, respectively. So these are previous results. In one dimension, Laban-Hambrook and Chen constructed such examples when B is smaller than or equal to A. And Laban-Hambrook also constructed such examples in higher dimension on the range B is smaller than A, and A and B are between D-1 and D. All these results are based on probabilistic construction. And this is our result. The range of P in the Mockenhaupt-Mitsis-Bak-Seeger restriction theorem is optimal if in one dimension if A and B are between 0 and 1 and B is smaller than 2A. So our construction is deterministic. And Mitsis proved that B larger than 2A cannot happen. So actually, we show the optimality for all possible A and B in one dimension. So before we give the idea of the proof of our result, let me briefly talk about the result by Laban-Hambrook and Chen. So in their results, they use two types of Cantor sets. One is a random Cantor set, and the other one is a Cantor set determined by arithmetic progressions. First, they consider the measure mu on the random Cantor set such that for any epsilon positive, measure of the interval is smaller than the length of interval to the power of A, and mu hat is smaller than c to the power of negative A over 2 plus epsilon. So that the exponent of the free decay, regularity and the free decay are both A if we ignore epsilon. Then they modified this measure so that this new measure mu is supported on the union of two Cantor sets. And the regularity is preserved, but free decay has changed from c to the power of negative A over 2 to c to the power of negative B over 2 for B smaller than or equal to A. And we can consider a sequence of functions f sub k supported on c sub d at the kth scale. So if P is smaller than 4d minus 4a plus 2b over b, LP norm of f sub k d mu hat over L2 norm of f sub k respect to the measure mu diverges to infinity as k increases. Thus, the range of P is optimal. In our work, we wanted to construct a deterministic example. So we used the set of well-approximable numbers instead of a random Cantor set. So what is the set of well-approximable numbers? Here's the definition. E of alpha is defined by a set of x in R such that absolute value of x minus R over Q is smaller than Q to the power of negative 2 plus alpha for infinitely many Q comma R in Z2. These sets arise from number theory, especially in Diophantine approximation. But they are also important in harmonic analysis since they are the only known deterministic examples of SLAM sets in R. SLAM set is defined as follows. A set E is a SLAM set of Hausdorff dimension A if there exists a measure mu supported on E such that mu hat is smaller than c to the power of negative A plus A over 2 plus epsilon for any epsilon. So A is the largest possible exponent for the free decay for any measure mu on E. In other words, if we choose B larger than A, there is no mu on E such that mu hat decays faster than c to the power of negative B over 2. In that sense, SLAM set is interesting. Kaufman proved that E of alpha is a SLAM set of Hausdorff dimension 2 over 2 plus alpha. So this is the only known deterministic example when the Hausdorff dimension of a SLAM set is not an integer. Yeah, so here's the idea of the proof of our result. Instead of a random Cantor set and a Cantor set determined by arithmetic progressions, we use the set of alpha well-approximable numbers E of alpha and the Cantor set C of beta determined by arithmetic progressions. And to extend the range from b smaller than a to b smaller than or equal to 2a, we gave a different weight on C of beta according to the parameter beta. Here's more detail. So this is about the construction of the measure. Mu sub k is a rapidly increasing sequence, and P sub m sub k is a set of primes such that P is between m sub k and 2 times of m sub k. B sub k is an odd number such that B sub k is between m sub k to the power of 1 plus beta and 2 times of m sub k to the power of 1 plus beta, where beta is between -1 and 1. If beta is 0, we choose beta sub k be in P sub m sub k. Otherwise, you choose beta sub k whole prime with any p in P sub m sub k. This is a definition of C of beta k, a C of beta. So C of beta is an intersection of C of beta k, where C of beta k is the set of x in the interval from -half to half, where x minus a over b sub k, absolute value of that is smaller than m sub k to the power of -2 plus alpha over 2, and a is an integer. Thus, C of beta is a Cantor set determined by arithmetic progressions. Let f be a Schwartz function supported on the unit interval, and let g sub k be as follows. This is quite long, and this is too long to carry around all the time. So let's say the first term is g sub alpha k, and the second term is g sub beta k. Then the functions g sub alpha k and g sub beta k are supported on E of alpha and C of beta, respectively. E of alpha can be considered as E of alpha k at the k scale, and C of beta can be considered as C of beta at the kth scale. Now let's look at g of alpha k more carefully. If x is 0, then g of alpha k at 0 is approximately m sub k to the power of 1 plus alpha. If absolute value of x is larger than m sub k to the power of -2 plus alpha, then g sub alpha k is smaller than m sub k to the power of alpha plus epsilon, which means g sub alpha k is too large near the origin. So we want to avoid the region. That's why we consider a Schwartz function, f naught, supported away from the origin. And let mu sub k be a product of g sub 1 to g sub k and multiply f naught. The function mu sub k weakly converges to a measure mu supported on E of alpha union C of beta, and this measure mu has desired properties. Let's move on to regularity and the Fourier decay. When you look at g of beta k, it has the factor 1 plus m sub k to the power of -beta. And that's the weight that we gave on the set C of beta k. Also note that g of beta k is supported on a m sub k to the power of -2 plus alpha over 2 neighborhood of an arithmetic sequence a over b sub k. So the weight on C of beta k is 1 plus m sub k to the power of -beta, which is bounded above by 1 if beta is non-negative, and it is bounded above by m sub k to the power of -beta if beta is negative. And the length of arithmetic sequence is that is b sub k, which is approximately m sub k to the power of 1 plus beta. And with this in mind, they give us the following Fourier decay and regularity and Fourier decay. If beta is 0, then measure of an interval is smaller than length of I to the power of 2 over 2 plus alpha. and mu hat is smaller than c to the power of negative 1 over 2 plus alpha, so that the exponents in the regularity and the Fourier decay are both 2 over 2 plus alpha if we ignore epsilons. If beta is positive, then the length of the arithmetic sequence is long, so that it lowers the exponent in the Fourier decay. So the regularity condition is preserved, while exponent in the Fourier decay has changed from 1 over 2 plus alpha to 1 minus beta over 2 plus alpha. If beta is negative, then the weight is large, so it lowers the exponent in the regularity condition. Note that we are only considering intervals of length smaller than 1. So weight is large, then it lowers the regularity. So when compared to beta being 0, it preserves the Fourier decay, while regularity exponent has changed from 2 over 2 plus alpha to 2 plus beta over 2 plus alpha. And this is about the failure of the L2LP estimate. We consider a smooth function supported on C of beta k as follows. Then it gives us the failure of the L2LP estimate. LP norm of f sub k d mu hat over L2 norm of f sub k respect to the measure mu diverges to infinity as k increases whenever p is smaller than 2 over 1 plus alpha minus beta over 1 minus beta if beta is non-negative. And the same thing diverges to infinity whenever p is smaller than 2 times of 1 plus alpha minus beta if beta is negative. So this is the summary of our result. If alpha is positive and beta is non-negative, then the measure satisfies the following regularity condition and the Fourier decay condition, while L2LP estimate fails on the range p smaller than 2 times of 1 plus alpha minus beta over 1 minus beta. Moreover, if beta is 0, mu is supported on E of alpha, which is the alpha well-approximable set of alpha well-approximable numbers. Similarly, if alpha is positive and if beta is negative, the measure mu satisfies the following regularity condition and the Fourier decay condition, while L2LP estimate fails if p is smaller than 2 times of 1 plus alpha minus beta. So how does this prove the optimality of the range of p? Let p be given as follows. P is smaller than 4 minus 4a plus 2b over b. And if b is smaller than a, we consider the case when beta is positive. So we choose alpha positive, beta between 0 and 1, and epsilon is sufficiently small so that a and b matches with the exponents in the Fourier decay regularity condition and Fourier decay condition respectively. So the exponent in the regularity condition is a, and the exponent in the Fourier decay condition is b over 2. And we can choose epsilon small enough so that 2 times of 1 plus alpha minus beta over 1 minus beta is between p and 4 minus 4a plus 2b over b. Then the measure satisfies the regularity condition and the Fourier decay condition for a and b respectively, but it doesn't satisfy L2LP estimate. If b is between a and 2a, we consider the case when beta is negative. So we choose alpha positive, beta between -1 and 0, and epsilon positive such that a and b matches with the exponents in the Fourier regularity condition and Fourier decay condition when beta is negative, and also consider epsilon sufficiently small so that 2 times of 1 plus alpha minus beta is between P and 4 minus 4a plus 2b over b. Then the measure mu satisfies the regularity and the free decay condition for A and B respectively, and it does not satisfy the L to LP estimate. So this proves the, this argument proves the range of P, proves that the range of P in the Mockenhaupt-Mitsis-Bak-Seeger restriction theorem is optimal in one dimension on the range where A and B is between 0 and 1, and B is smaller than 2a. And our next project is to prove the optimality of the range of P in higher dimensions. So in the proof in one dimension, we use that the set of well-approximable numbers, since it is an explicit SLAM set in R. And there are results about explicit SLAM sets in higher dimensions. Hambrook constructed an explicit SLAM set in R2, and Fraser and Hambrook constructed explicit SLAM sets in all higher dimensions. So we are hoping to achieve our goal by using these explicit SLAM sets in higher dimensions. All right, so this is all for my talk. And if you have any questions, then feel free to reach out to me. Here's my email. So I'll stop here, and thank you for listening.